The shift from task-specific edge pipelines to token-based edge-cloud collaboration has fundamentally changed how we deploy multimodal foundation models. Edge devices now encode visual observations into dense token sequences and transmit them to a general-purpose cloud, LLM, for reasoning. But that flexibility comes with a steep efficiency penalty. Vision encoders preserve patch-level representations that are heavily redundant, and processing the full visual sequence bloats the multimodal context window, skyrocketing cloud-side compute. Visual token pruning is mandatory for scalable deployment, but existing methods struggle in distributed settings. Vision-driven approaches are query-agnostic and routinely discard subtle but answer-critical regions. Query-guided methods work, but they typically require the full visual sequence to enter the decoder, rely on the cloud model's internal states, or demand autoregressive answer generation. Compact proxy models offer a path forward, but many still aggregate attention across every query position or run repeated visual encodings, adding latency that negates the edge cloud advantage. So how do you extract a query-conditioned relevance signal at the edge, without cloud access, autoregressive loops, or heavy aggregation? The researchers behind LLaVA built a training-free framework around a single, well-understood transformer property, causal attention masking. Under causal masking, the final token in a sequence can attend to every preceding token. That means the last query token in your prompt has already processed the complete image prefix and the entire question. Its attention distribution over the visual tokens isn't a partial snapshot. It's a compressed, query-conditioned relevance signal that captures the full image query context. LLaVA leverages this by running a compact edge-side VLM, performing a single decoding-free prefill pass, and extracting attention solely from that last query position. Let's break down the mechanics. The edge and cloud models share the exact same vision encoder and spatial tokenization layout, but they use separate token-wise connectors. This one-to-one interface means visual tokens selected at the edge can be projected directly into the cloud connectors embedding space without feature alignment or image re-encoding. Once the edge model assembles the multimodal prompt, it runs through the transformer layers. LLaVA reads the attention weights from the last query position across all layers and heads. If you have L layers, H heads, and N visual tokens, aggregating scores from just that one position requires O, LHN operations. Compare that to averaging across M query tokens, which scales to O LHMN, and the edge overhead becomes negligible. In practice, LLaVA extracts these important scores in roughly 2.5 milliseconds. Raw attention scores, however, aren't sufficient for token selection. If you simply retain the top K highest scores, you'll end up with a dense cluster of tokens covering the same semantic region, wasting your fixed token budget on redundancy. LLaVA solves this with an importance-weighted greedy K-center selection strategy. It initializes the selection by locking in the single most query-relevant token. For each subsequent iteration, it computes the coverage distance to all already selected tokens, and picks the unselected token that maximizes the product of its query relevance score and its marginal coverage gain. This multiplicative objective naturally suppresses tokens that are either irrelevant to the prompt or highly similar to already chosen patches. After K iterations, the selected indices are restored to their original spatial order and transmitted to the cloud. The cloud model consumes them through its native connector and generates the final response. All parameters remain frozen throughout. The empirical results validate this approach. Across 11 multimodal benchmarks, LLaVA consistently outperforms query-agnostic baselines like VisionZip and FastV, as well as query-dependent methods including FastV, sparse VLM, and SGP. At a severe 12.5% token retention rate, LLaVA preserves 95.4% of full token accuracy. That's a substantial margin over the best query-agnostic method, which drops to roughly 73% under the same budget. More importantly, LLaVA maintains a highly competitive efficiency score. While query-agnostic methods technically achieve lower edge latency by skipping aggregation entirely, their accuracy degrades sharply under aggressive pruning. LLaVA strikes the optimal balance, cutting cloud-side flops by nearly 90% while keeping performance within striking distance of the unpruned baseline. The framework also generalizes cleanly across model families. When instantiated with LLaVA 157B as the edge proxy and LLaVA 1513B as the cloud target, LLaVA retained 90.2% of full performance at a 94.4% token reduction, confirming that the method is robust to different visual token interfaces and connector designs. Ablation studies further isolate why this design works. Replacing the last token signal with attention from the first or middle query positions degrades performance, while averaging across all query tokens or incorporating autoregressively generated answer tokens yields only marginal gains at the cost of significantly higher edge latency. The K-center selection strategy also proves critical. Swapping it for a simple top K ranking drops accuracy by over 4 points on chart QA and nearly 40 points on MME at 12.5% retention, demonstrating that jointly optimizing for relevance and feature diversity is necessary to make aggressive token budgets viable. LLaVA demonstrates a fundamental principle of efficient system design. You don't need massive proxy models, complex training loops, or cloud-side feedback to achieve query-aware pruning. You just need to recognize where the relevant signal already exists in the architecture. By exploiting causal attention's inherent context bundling property, LLaVA delivers lightweight, training-free token selection that slashes transmission payloads and cloud compute without sacrificing reasoning capability. As multimodal AI continues to push into distributed, resource-constrained environments, methods like this will be essential for keeping the edge cloud interface scalable. The full paper, including detailed efficiency measurements and cross-dataset ablations, is linked below. Thanks for watching.